Hello everyone, my name is Daryl Markowitz and I'm coming to you from Ontario, Canada. I was unable to attend the session for the obvious political reasons. What I want to talk to you today is about a series of 11 experimental iron smelts that were undertaken here between 2007 and 2024, where we were attempting to recreate the process that was used at a site in Iceland dating to the Viking Age called Háls. Háls is located at what would be considered in west central Iceland, and it was excavated by Kevin P. Smith in the late 1990s and documented to him in his 2005 paper. I had met Kevin at Lasso Meadows, Newfoundland, where we were both working on the Vinland site. We happened to be staying at the same B&B. We struck up a friendship, and Kevin has been a close advisor and mentor to me through all the work. During the Háls series, we also referenced a site in far western Iceland, excavated by Margrét Hamelsdottir, who also we had corresponded with during her work around 2012, which had resulted in her also undertaking a test smelt. There was some reference to the Skogar site in far northern Iceland, with the documentation there coming out in 2013. Háls is a long-duration farming site. However, there have been repeated incidents of iron smelting on that site, starting in 870 and running through to the late 900s. This has been broken into two major use campaigns, dozens of individual smelts undertaken as indicated by massive piles of slag. There is evidence of both reuse of existing furnaces and building of new ones. One of the problems facing Icelanders is that there is no naturally occurring clay, or very little of it, available on volcanic Iceland. So they had to come up with a new way of creating the fireproof containment that iron smelting requires. The solution indicated at Háls is using conical stacks of cut turf. Starting in 2007, my team attempted to take Kevin Smith's interpretation of the archaeology and convert it into a practical working system. The archaeology suggested, as I've already said, a conical turf as the primary support for the structure. Kevin had proposed, due to the evidence in the archaeology, that there had been a timber box framing and an earth-filled platform surrounding these conical structures. The archaeology indicated that the diameter of the furnaces was between 20 to 35 centimeters. And there was some use of clay as a liner inside the sod, with fragments remaining up to 3 centimeters in diameter. There was an indication of use of stone in the front part of the furnace, and there was one fragment found that had a partially circular outline on it, suggesting an opening at 5 to 6 centimeters of a blast hole system. We'll come to that later. Things that were missing in the archaeology: there's no indication whatsoever of what the terrier might have been used, what the material was, how it might have been applied to the furnace. Exactly how the slag would have been controlled that's generated inside the furnace was completely uncertain, because the bellows would have to sit very, very close to the front of the furnace. The actual size and structure of that bellows was completely unknown and remains completely unknown for Viking Age. How the extraction was done, again, was a little bit uncertain from the remains. Some of the remaining slag bowls in place in the furnaces suggested a bottom front extraction, but the other possibility, because of the working platform that Kevin had proposed, was that it would have been a top extraction with people standing over the top of the furnace. My direct work with bloomery iron smelting had started in 2001. And by 2007, when we started this campaign, I'd undertaken 25 individual smelts. Through the main bulk of this series of work on Háls, 2007 to 2016, I had done a further 45 iron smelts. And by the time we got to the last in this series in 2004, it was actually number 98. Over this time, we had developed here a practical working system that was defined by a freestanding clay cylinder made of a mixture of shredded horse manure, sand, and high-temperature clay, with walls set at 5 to 8 centimeters thick, typically a 25 centimeter interior diameter. Furnace is normally about 60 to 70 centimeters tall. This would produce an interior active stack of about 40 centimeters, which we consider to be a minimum, and left us 15 to 20 centimeters in the base for the collection of the slag bowl and the formation of the bloom. We had initially used steel pipe terriers, but we had switched to pre-made ceramic and eventually adopted use of a forged copper terrier. We had learned that the ideal down angle for these terriers was between 20 and 25 degrees, typically inserted 5 centimeters into the body of the furnace. We had been using primarily electric blowers for our air delivery, although there had been experimentation with using replica Viking Age bellows systems. Through all this, we developed a standard working sequence of addition of ores and charcoal and how much air was being applied to the furnaces. We were routinely working with about 25 kilograms of ore, which is this series would be to those volumes. And in 2008, we had developed artificial bog ore using a red iron oxide powder that had an elemental iron component of approximately 55%. We had been able to generate predictable yields in the range of about 20% using this system. The first group of 2 experiments in 2007 involved testing of a build using stone slabs and what we call a blowhole design. In a blowhole, there's a gap in the front of the furnace, in this case typically 5 to 6 to 7 centimeters wide, with a steel pipe terrier that's set outside of the furnace itself, and the air is then thrust into this gap. The slag was controlled by a large space underneath the terrier, 18 to 20 centimeters, and for these first tests we were using a granular hematite ore, which was quite high in elemental iron content. What we discovered is that with this system we were getting fairly poor penetration of air into the interior of the furnace, and because of that the heat was washing quite heavily over the front of the stone, and this resulted in heavy erosion of the granite stone that we were using here. Another feature of this is that we found the internal slag bowl was sitting up much too high and threatened to drown the air intake before a major bloom had been formed. This may be as much due to our inexperience with this particular technique as anything else. The next group of 3 experiments would concentrate on the work layout suggested at Háls. There would be an interruption between the first 2 in 2008 and the last one in 2012, when the team was concentrating on work based on Vinland for Parks Canada. So we established a 2 by 2 meter outline suggestive of the turf box. We had a natural occurring bank that we could dig into. So these furnaces were partially earth banked with a V-shaped slot at the front. These would be full clay cylinders with no use of sod, and we were still trying to get the bugs out of the blowhole system. In some cases we had to convert to insert terriers partway through the process when the slag bowls got too high. Through this series we were also gradually reducing the thickness of the clay walls from our standard 5 to 8 centimeters down, in this case, to 4 centimeters thick. The first 2 smelts would use industrial taconite and then granular hematite as the ores. By number 51 we were routinely using our red iron oxide analog. The main takeaway from this series was that attempting to work standing over top of the furnace, as you can see here, was just physically extremely punishing. For the Group 3 experiments in 2015, we were attempting to work with sod as a construction material. Now, we were cheating a little bit because we just cut a larger hole inside of our existing earth bank and laid the sods in that area. The method we were using is we were stacking up the sods against the metal form, as you can see here, and then we were reaching down inside to apply the clay liner. As it turned out, just due to short time, number 61, we didn't actually use any clay liner at all. It was just the sods themselves. When we got to experiment number 70, we had reduced the thickness of the clay walls down to 3 centimeters, consistent with Háls. All of these smelts used a prepared ceramic tubular terrier, and again we were using the dark dirt analog ore. What the surprise was that number 61, that had no cleaner at all, proved effective for a single smelt. The sods seemed to hold together through the sequence of generating the iron, but then collapsed into themselves as the charcoal burned away in the center. We also discovered that as the clay was getting thinner and thinner, attempting to apply it to the outside of the turf itself was getting more and more difficult. The clay would stick to your hands as much as it would actually stick to the earth in the sods. Smelt number 7 was a complete build of the Háls system with the turf box and the earthen platform. The build was done by Richard Schweitzer at Laurel, Ontario, about 50 kilometers south of Wareham. One of the problems was that inexperienced hands created a lot of irregularities in the form of the construction. Richard had considerable problem applying the thin clay as it happened at times before. And this resulted in collapsing of the interior walls and creation of far too much slag. It also pointed out an important difference between the composition of grass sod, even here in Ontario between two locations, and what was suspected would be the soil structure in Iceland, volcanic soils with entirely different kinds of vegetation. This particular smelt would result in the porous yield of the entire series at only 10%. There'd be another gap in the Háls series with work on Pictish and stone builds, and also experiments with Viking Age bellows systems. At this point, I decided to go back and revisit the original interpretation of the Háls information in light of the acquired experience we'd had since our original assessment in 2007. So I went back to the original excavation drawings and took a process where I took those illustrations and kind of graphically straightened up the turf layers to look at the thickness and the lines to determine the possibility that, in fact, there was a cone without a timber frame on the outside, and that the pad defined in the original archaeology might actually just have been the turf that was sliced up to build the actual conical structure. We certainly had proof that with number 70 that the elevated platform was not required at all to actually physically manage the furnace. There had also been a question about the possibility that Háls had used a durable copper or wrought iron terrier, which of course would have been a preserved piece of equipment and unlikely to show up in the archaeology. Another question was where the bellows would have physically been placed, taking into account the possibility that reinforced leather might have been used to create hosing to keep the bellows away from the front of the furnace. On a fairly recent trip to Iceland, Michelle Hare-Smith had been able to gather some samples of a clay-like material close by physically to Háls. We had this analyzed by team member Marcus Burnham, and then we went to Commercial Pottery Supply and analyzed the components that would generate a similar composition. So we had kind of like a Icelandic analog clay. And we tested this by creating a series of 4 centimeter diameter cylinders and putting them in a propane gas forge at 1070 Celsius for 90 minutes. And I had made up 4 separate mixtures, one of the clay with no additives, one with clay and 35% of a copper slag added to it, which I had on hand. A third one with 50% clay, 50% sand, a more likely composition, and a third using our routine mixture of clay, sand, and shredded dry horse manure added in thirds. And the results were quite outstanding in that the clay, sand, horse manure proved to be quite durable, both in terms of its heat resistance and its actual structural strength, whereas the straight clay with no additives literally was disintegrating even at temperatures of 1070, which are well below the kind of operating temperatures of an iron smelting furnace. So what we call the phase 3 work involved creating a conical grass sod furnace without any framer packing, and it was set on a clean sand pad. We used the Icelandic clay manure cob mix for the structure of the inner liner. The first furnace that was built was 4.5 centimeters average wall thickness. We used a different building technique where interior form was used. The clay was pushed against the form. Once it had been built up to a certain height, typically about 30 centimeters, then the sod would be placed on the outside and the form removed. And then that process would be repeated as we built up. That got over the problem of the clay sticking to the hands more than to the sods. In total, this furnace required 11 square meters of sod. The first experiment in 88, would use the copper insert to rear, and again the analog. What was discovered here is that there was no problem whatsoever standing on the ground outside of the cone of sod and reaching over with handled tools to apply or probe down the interior or add charcoal. This particular smelt got a larger bloom than we really expected, and because of that we hadn't created a large enough front arch area to actually extract that bloom, so there was additional damage. The Icelandic clay mix had no problem surviving the higher interior smelting temperatures, which can range up into 1450 Celsius. This would never happen in Iceland. We came out the morning after Smelt 88 to find that a 20 centimeter long snapping turtle had crawled into the warm furnace in the early hours of the morning and knocked a big piece out of the front of the furnace. The red line you can see here indicates the damage that was done during the extraction process. The rest of that mess was caused by that turtle. Smelt 89 would be a reuse of the earlier furnace after it had been exposed to the summer rains for 2 months. What we discovered is there had been considerable slumping of the sods themselves, which you can see in this illustration. We pretty much had to rebuild the front of the furnace using clay in the gaps you can see, and creating a new stone block arch at the bottom. The smelt would use the copper to rear again, along with the analog. And what we discovered is there was a considerable problem matching up the new clay to the existing structure of the liner. This allowed way too much broken sand from the sod to leak into the inside of the furnace, and because of that we really had to do a lot of aggressive modifications of the slag bowl in the smelt. Smelt 98 would be 2 years later. The furnace had been left with a small plastic cover over the mouth of the furnace, but otherwise unprotected through 2 Ontario winters of freeze and thaw. There had been considerable slumping of the sods over this period, and most importantly, the shaft itself had slumped forward 20 degrees. Although the clay liner had appeared to have preserved itself, When we attempted to shift it forward to a vertical position, we found it broke into 3 major sections. The front section of the furnace had pretty much broken apart, so it was replaced with a series of stone blocks. The large remaining portions of furnace liner were patched together with fresh clay. The top edge of the existing furnace had become very, very ragged from freeze and thaw, so a sequence of stones was placed around the top of the turf to extend the line of the furnace. A ceramic terrier would be used for this particular smelt. There had been a separate series ongoing at this point to try to develop a mechanical analog for the kind of air delivery that would come from a Norse twin-chamber bellows. And we had created a mechanical plate that slid back and forth that gave the same kind of pulsing air delivery. The effect of this, however, is always that there's reduced penetration into the inside of the furnace. This means that the slag bowl itself tends to develop too high, and in this case there was considerable failure of the interior liner. This smelt would have a very bad yield of only about 6%. The image also shows you how easy it is for the workers to stand to one side of the conical stack and just reach over with a handled tool to deliver, in this case, ore addition. The next logical step in this series would be to repeat this process in Iceland itself. But as independent researchers, without institutional support, this is just financially impossible. What have we learned from this process? Most importantly is the conical turf build has been proved to be completely viable. Also, that the sod cone itself doesn't require a frame and platform to make the system functional. The Icelandic clay sample, at least as we had provided to us, does withstand the temperatures inside of a smelting furnace. However, composing a liner below 3.5 centimeters we found extremely difficult. It always has to remember the standard problems of the impact of quality of ore and the impact of the air volumes have on the results in a smelt. We're quite aware of the geographic limitations of using materials and process from Ontario as opposed to those available in Iceland. Of course, there's the huge difference between using a mechanical electric bloater versus human-powered bellows to be considered. Important things to remember for any experiment are the use of standardized records, which wasn't the case over the life of this series, and of course, only test one variable at a time. This presentation is only a fast overview of the more detailed report that was published in 2024, which is available on Kindle Amazon if anyone was really interested. I'll also point out that the full documentation of our entire 25 years of iron smelting experience is available on the website indicated here. I'd like to thank members of the Dark Ages Recreation Company who have supported this work through their labor, through the entire process. If anyone is really interested in talking about iron, please take down my email and contact me. Thank you very much for your attention today.